Welcome to Section 6, Lesson 9. In the previous lesson, we set up systems of inequalities and identified their feasible regions and corner points. Today, we add an objective function on top linear programming, which finds the best feasible point under a stated optimization criterion. The corner point theorem of linear programming says that the optimum of a linear objective over a feasible region defined by linear constraints always occurs at one of the corners of the region. So the practical procedure reduces to evaluating the objective at every corner and picking the corner that maximizes or minimizes the value as required. Today we lock in the 4-step procedure and walk through one maximization example illustrating the standard linear programming workflow. First idea on the board. A linear programming problem has 3 pieces. The objective function is a linear expression in the decision variables that we want to maximize or minimize, like profit equals 5x plus 7y or cost equals 3x plus 2y. The constraints are linear inequalities in the decision variables that define the feasible region, like the resource constraints we covered in the previous lesson. The decision variables are the unknowns x and y that we are choosing values for, often subject to non-negativity constraints when the variables represent physical quantities like production amounts or volumes. Second idea. The corner point theorem of linear programming states that the optimum of a linear objective over a polygonal feasible region defined by linear constraints always occurs at one of the corners of the region, called the vertices. The theorem is foundational because it reduces the optimization from searching over the entire continuous region to evaluating the objective at a finite number of corner points. 2 variable LP problems with 3 or 4 constraints typically have 3 or 4 corners, and checking all of them is fast. The 4-step procedure for solving a linear programming problem is Step 1. Graph the feasible region defined by the constraints. Step 2. Find all the corner points by solving boundary systems pairwise. Step 3. Evaluate the objective function at each corner. Step 4. Pick the corner that gives the optimum value, maximum if the problem says maximize and minimum if it says minimize. The corner evaluation step uses the function evaluation skill from Section 5, Lesson 2, applied to the objective function at each vertex coordinate. Today's worked example illustrates the workflow on a standard textbook profit maximization problem. Linear programming maximizes or minimizes a linear objective function subject to a system of linear constraint inequalities. The decision variables are the unknowns we choose. The constraints define the feasible region of allowed choices, and the objective specifies which choice we prefer. Here is the corner point theorem. The optimum of a linear objective over a polygonal feasible region always occurs at one of the corner points or vertices of the region. Geometrically, the theorem follows from the fact that linear objectives produce parallel level curves, and the level curves can be pushed in the optimization direction until they last touch the feasible region at a corner. The corner where the last touch happens is the optimum. Step 1 in the 4-step procedure. Graph the feasible region using the system of inequalities technique from the previous lesson. Each constraint contributes a half plane, and the feasible region is the intersection of all the half planes. Draw the boundary lines, shade the intersection, and outline the polygonal feasible region clearly. Step 2. Find all the corner points by solving boundary systems pairwise. Each pair of constraint boundaries that intersects inside or on the feasible region produces a corner. Use substitution or elimination to find the exact coordinates of each corner. The corner finding work uses the system solving methods from earlier in this section directly. Step 3 is evaluate. Compute the objective function value at every corner point. Plug each corner's coordinates into the objective expression and simplify to a number. The list of objective values, 1 per corner, is the candidate set of optimal values, and the actual optimum is one of them by the corner point theorem. Step 4 is select the optimum value, the largest if maximizing, the smallest if minimizing. Report the optimal corner and the optimal objective value as the answer. Here is the worked example. A factory produces tables and chairs. Each table requires 3 hours of labor and uses 2 units of wood. Each chair requires 1 hour of labor and uses 1 unit of wood. The factory has 24 hours of labor available and 12 units of wood. Profit is $40 per table and $20 per chair. How many tables and chairs should the factory produce to maximize profit? Step 1. Define decision variables. Let x equal the number of tables produced and y equal the number of chairs produced. Both are non-negative integers in principle, though linear programming usually treats them as continuous and rounds at the end. Step 2. Write the constraints. Labor 3x plus y less than or equal to 24. Wood 2x plus y less than or equal to 12. Non-negativity x greater than or equal to 0, y greater than or equal to 0. For inequalities total, define the feasible region. Step 3. Write the objective function. Profit p equals 40x plus 20y. We want to maximize p over the feasible region. Step 4. Graph the feasible region. The non-negativity constraints restrict to the first quadrant. The labor constraint draws a boundary line through 8, 0 and 0, 24. The wood constraint draws a boundary line through 6, 0 and 0, 12. The feasible region is bounded by these 4 lines. Step 5. Find the corner points. The corners are the origin 0, 0, where x and y-axis meet, 6, 0, where the wood line meets the x-axis, 0, 12, where the wood line meets the y-axis, and the intersection of the labor line and the wood line. Solve the labor and wood lines. 3x plus y equals 24 and 2x plus y equals 12. Subtract x equals 12. Wait, let me recheck. Subtracting the second from the first gives x equals 12, which is outside the feasible region, because at x equals 12 the wood constraint requires y less than or equal to 12 minus 24 equals negative 12, which violates y greater than or equal to 0. So the labor and wood lines intersect at 12, negative 12 outside the feasible region. So that pair intersection is not a corner. Let me redo by checking which constraints form actual corners. Actually, let me reconsider the wood line caps y much earlier. With wood x-6 at eta 0 and y-12 at x-0, the wood line is the binding one at low x, the labor line is binding higher. They intersect outside. So the actual feasible region has corners at the origin 6, 0 and 0, 12. The labor line is non-binding at the wood feasible region within the first quadrant. Step 6. Evaluate the objective at each corner. At 0, 0 p equals 0. At 6, 0 p equals 40 times 6 plus 20 times 0 equals 240. At 0, 12 p equals 40 times 0 plus 20 times 12 equals 240. 2 of the 3 corners tie at 240. Step 7. Identify the maximum. Both 6, 0 and 0, 12 give profit 240, so the maximum is 240 achieved at either of these corners. The factory can produce either 6 tables and no chairs or no tables and 12 chairs, both producing the same profit. Any combination on the wood line boundary segment between these 2 corners produces the same profit because the objective is parallel to the wood constraint in this special case. Profit equals $240 maximum. So the maximum profit is $240 achieved by either 6 tables, 6, 0 or 12 chairs, 0, 12. The big lesson from this example is the 4-step procedure: feasible region, corner points, objective evaluation, optimum selection. The corner point theorem reduces the optimization to a finite check at the vertices, regardless of how complex the feasible region is. Linear programming is one of the most widely used optimization techniques in applied math, and the algebra level workflow you learned today is exactly the workflow used in industrial linear programming software, scaled up to many variables and many constraints. Here is a second example illustrating a minimization problem. A nutritionist designs a diet using two foods. Food A costs $3 per unit and provides 10 units of vitamin and 4 units of protein per unit. Food B costs $4 per unit and provides 5 units of vitamin and 12 units of protein per unit. The diet must provide at least 50 units of vitamin and 48 units of protein. Minimize the cost. Step 1. Define variables. Let A equal units of food A, B equal units of food B, both non-negative. Step 2. Write the constraints. Vitamin 10 A plus 5B greater than or equal to 50. Protein 4 A plus 12B greater than or equal to 48. Non-negativity A greater than or equal to 0. B greater than or equal to 0. The first two are greater than or equal to constraints, producing a feasible region above and to the right of the constraint lines, unbounded extending up and right. Step 3. Write the objective cos C equals 3A plus 4B to be minimized. Step 4. Find the corner points of the feasible region. The corners are intersections of constraint boundaries within the first quadrant. Vitamin line at the y-axis at A equals 0, 5B equals 50, so B equals 10. So 0, 10 is a corner. Vitamin line and protein line intersection. Solve 10A plus 5B equals 50 and 4A plus 12B equals 48. Multiply first by 12, 120A plus 60B equals 600. Multiply second by 520A plus 60B equals 240. Subtract 100A equals 360, so A equals 3.6. Back substitute 10 times 3.6 plus 5B equals 50, B equals 2.8. Corner 3.6, 2.8. Protein line at x-axis at B equals 0, 4A equals 48, so A equals 12. Corner 12, 0. 3 corners total of the bounded portion of feasible region near the constraint intersection. Step 5. Evaluate cost at each corner. At 0, 10 C equals 3 times 0 plus 4 times 10 equals 40. At 3.6, 2.8 C equals 3 times 3.6 plus 4 times 2.8 equals 10.8 plus 11.2 equals 22. At 12, 0 C equals 3 times 12 plus 4 times 0 equals 36. 3 values 40, 22, 36. Step 6. Identify the minimum. The smallest value is 22 at 3.6, 2.8. So the minimum cost is $22, achieved by buying 3.6 units of food A and 2.8 units of food B. So the minimum cost diet uses 3.6 units of food A and 2.8 units of food B for a total cost of $22. The big lesson from this example is that minimization problems work the same way as maximization, just selecting the smallest objective value at the corners instead of the largest. The greater than or equal to constraints produce unbounded feasible regions extending outward, but the bounded portion near the constraint intersection contains the optimal corner. Real-world cost minimization problems in nutrition, manufacturing, and logistics use this same pattern, often scaled up to many ingredients or many products with many constraints, but the algebra level workflow stays the same. 3 mistakes that catch every algebra student during their first weeks of linear programming work. Each one is fixable with a small explicit habit applied on every problem. First mistake. Missing a corner of the feasible region and therefore missing the actual optimum value. A student finds 3 corners by inspection and evaluates the objective at all 3, missing a 4th corner where 2 boundaries intersect inside the region. The fix is to systematically check every pair of boundary lines for an intersection point, including the non-negativity boundaries with the constraint lines, and to verify whether each intersection is inside the feasible region. Pairs whose intersection is inside are corners, pairs whose intersection is outside are not. The systematic check ensures no real corner is missed. Second mistake. Picking the wrong corner because of confusion between maximization and minimization. A student in a profit problem picks the corner with the smallest objective value, when the problem asks to maximize, or in a cost problem picks the corner with the largest value when the problem asks to minimize. The fix is to read the problem statement carefully one more time after evaluating the objective at all corners, and to confirm which direction of optimization is required before selecting the optimum corner. Third mistake: attempting to maximize an objective on an unbounded feasible region where the objective has no upper bound. A student sets up a problem with no maximum corner because the feasible region extends infinitely in the direction the objective increases. The objective grows without bound, and no finite maximum exists. The fix is to check the feasible region's boundedness in the direction of the objective gradient. If the region is unbounded toward the optimization direction, the problem has no finite optimum. Real-world problems with this structure are usually missing a constraint and need additional bounding to make sense. Linear programming is one of the most widely used optimization techniques in applied math, with applications in operations research, supply chain management, finance, and many other fields. 4 broad sectors below. In operations research, linear programming is the founding technique invented in the 1940s to solve resource allocation problems efficiently. Production scheduling, capacity planning, and workforce assignment all rely on linear programming continuously. The simplex algorithm developed by George Dantzig in 1947 is still the workhorse algorithm of commercial LP software, and it is essentially a systematic version of the corner evaluation procedure you learn today scaled to many variables. Modern industrial LPs handle systems with thousands or millions of variables and constraints. In supply chain management, decisions about how to route trucks between warehouses, how much inventory to allocate to each distribution center, and how to distribute production across factories all reduce to large linear programs. Companies like Amazon, FedEx, and Walmart run linear programming software continuously to optimize their logistics, with each LP solving in seconds despite the millions of variables involved. The mathematical foundation is exactly the corner point theorem from today. In finance, portfolio optimization allocates capital among investment assets subject to constraints on total investment, risk tolerance, and sector limits. The classical Markowitz portfolio model is a quadratic programming problem rather than strictly linear, but many constraint formulations reduce to linear programming, and the linear programming concepts from today are the conceptual gateway to all of modern portfolio theory. In diet and nutrition, the Stigler diet problem from 1945 asked for the minimum cost diet meeting nutritional requirements, and linear programming provided the answer. Modern dietary planning for hospitals, athletes, and dietary intervention studies still uses linear programming on systems with many ingredients and many nutritional constraints. The 2-variable example we covered today is the toy version of the same problem at scale. 3 things to take with you from this lesson today. Linear programming is one of the most widely used optimization techniques in applied math, and the algebra level workflow scales directly to industrial scale applications in operations research, finance, and supply chain optimization. First, a linear programming problem has 3 pieces. The objective function is a linear expression to maximize or minimize. The constraints are linear inequalities defining the feasible region of allowed decisions. The decision variables are the unknowns whose values we choose to optimize the objective subject to the constraints. The 3 pieces together specify the optimization problem completely. Second, the corner point theorem of linear programming says that the optimum of a linear objective over a polygonal feasible region always occurs at one of the corner points or vertices. The theorem reduces the optimization from a continuous search over the entire region to a finite evaluation at the corners, which is what makes linear programming computationally tractable. The simplex algorithm in industrial LP software is essentially a systematic corner walking procedure built on this theorem. Third, the 4-step procedure is graph the feasible region, find all corner points by solving boundary systems pairwise, evaluate the objective function at each corner, and pick the corner with the optimal objective value. Maximum if the problem says maximize, minimum if it says minimize. The procedure is mechanical once practiced and produces exact optimal solutions reliably for any well-posed 2-variable linear program. Coming up next, the lesson called Section 6 Marathon, where every system solving technique from Section 6 is applied back-to-back on a mixed sequence of problems covering substitution, elimination, 3-variable systems, special cases, word problems, systems of inequalities, and linear programming. The marathon is the natural completion of Section 6 and the practice format that builds the speed and pattern recognition needed for tests, contests, and applied work.